Good morning, students. So I hope you can see my screen. So we were talking about Boxcox transformation, if you can remember. So we were talking about the difficulties that you face when you are fitting a multiple linear regression model. So we were talking about the Boxcox transformation. Now, especially when you have heteroscedasticity, and also when the dependent variable is not normally distributed, in order to overcome that, we can use this Boxcox transformation. So what we do in this Boxcox transformation is you have to take your dependent variable, and then we have to change our dependent variable using a transformation. Now, for an example, in early days, when this Boxcox transformation was introduced, if you take your dependent variable as y, it can be transferred as y to power lambda minus 1 over lambda when lambda is not equal to 0. And it can transferred as log y when lambda is equal to 0. So this was the first Boxcox transformation which was used when they introduced this transformation back in 1964. With this transformation, there were some problems because when your dependent variable has negative values, there were problems occurred with this transformation. So what they have done is they have used some other transformations. So this is also another Boxcox transformation that you can use in order to transfer your dependent variable to remove non-normality and the heterogeneity. So in this case, what we do is here you can see your dependent variable y. You can transform your dependent variable using these two equations. And here, when you use this Boxcox transformation, you have this parameter lambda. So when you take this parameter lambda, so you have to find what is the most optimal value for lambda. So to find the optimal value for lambda, we can use this equation. You can see the equation E. So what you can do is now when you fit your regression model, you can obtain the sum of square error, and then you can take your y values, and you can change this lambda value and find the value of this equation E. So for the value which maximize this L lambda equation, you have to select the lambda value which maximize this L lambda equation, and that would be the optimal lambda value to take your to perform your Boxcox transformation. Now, actually, there are different transformations that you can use when your dependent variable is not normally distributed. And when you have heterogeneity, and but if you just go through some of the research papers, and if you just read some of the references, you will see when they're using the Boxcox transformation, these are some of the common transformations that they are using. So when you take lambda as -3, most of the researchers have used 1 over y to power 3 as for your transformed data. So here I have taken some of the common transformations that you can apply when you are doing the Boxcox transformation. We'll do one example and see here. So in this case, I'll do Boxcox transformation. So before moving to the next one, I'll show you how to do the Boxcox transformation manually and as well as using R. Give me a second. Okay, so let's do Boxcox transformation. Now in this case, let's say first we are going to define our variables to perform this Boxcox transformation. This is a very basic example I'm going to use here. So in this case, let's say we have a variable y. So I'm going to enter these values for y. So this is our y variable, and we have another variable x. So for x, we have these values. We have 7, let's say 7, 8, 3, 2, 4, 4, 6, 6, 7, 5, 3, 3, 5, 8. Okay, so we want to perform, let's say we want to run a regression model using this these two variables, x and y. So let's take model 1 as the name of our linear model. So in this case, we can just run a model using our two variables, x and y. So if you want to check the model summary, now you know the built-in functions in R. You can use the function summary and give the name of the model. So here you can see the model summary. In this case, what are the variables and all you can see. Okay, so in this case, here I'm not going to show you how to test the assumptions of the model, but we know after fitting the model, you have to check for model assumptions and check whether the normality assumption is violated or not, whether the errors are having a constant variance. Those things you have to perform, but that part I'm not going to do. Now let's assume for this model, the assumptions are violating. Let's say the normality assumption is violating. So in that case, we can use the Boxcox transformation. So if you're going to use it manually, what you have to do is you have to select a transformation that you are going to use, and you have to select a lambda value, and you have to just change your lambda value and fit your model and check whether the model assumptions are violating or not. So as I showed you, there are very commonly used Boxcox transformations. So as for an example, if you take lambda value, let's say you're going to take the lambda value as -2. So in this case, let's say you're going to take the lambda value as -2. So in this case, the transformation that we can use, let's say for y, we are going to use the transformation as 1 over y squared. So now in this case, y I have transferred into y over 1 over y squared. So now what you can do is, now this is your new response variable, right? So for the new response variable, when you fit the regression model, so I'll take this as model 2. Now we have changed y. So now you can use this model to fix the regression. And then what you can do is, again, you can check the model summary. And in this case, you can check the model assumptions as well. Now, this is just a random value that I used for lambda. Now, here you can see but I have in the previous model, when we just take the y values and when you just fit the model, when you take the model summary, just take here, when you take the first model, you can see the intercept and the coefficient of x variable, both are not significant. But in the second model, after using a random Boxcox transformation here, we can see yeah, so here you can see the coefficient of x, that is beta 1 parameter, it has become significant. So this is just a random transformation that I have applied. So when you're doing, especially when you are doing a research, when you want to transform your data, you can check for different lambda values and apply that to your data and see what will happen, whether your coefficients are getting significant and whether model assumptions are violating or not. So in this case, after fitting your model, you have to check for the normality assumption and for the heterogeneity, that is whether the errors are having constant variance or not. So that those things you have to do. And also in R, if you are using R, if you can use the built-in function to perform this Boxcox transformation as well. You don't have to do this manually, but let's say in the exam, if I ask you to perform, if I give you two variables, x and y, I can ask you to fit the regression model for x and y, and I can ask you to apply a given transformation, and I can ask you to check the significance of the coefficient. So in that case, this is how you do it manually, because we know how to find the coefficients manually by now when you're fitting the regression models. So let's say we are going to use R to do this Boxcox transformation. So I'm going to take the same set of variables. Let's say we have x and we have y. So if you're going to apply the Boxcox transformation, the first thing that you have to do is you have to use the original data set, and then you have to fit the regression model using the original data set. So we have done it already. We have taken our model 1 to fit a regression model between x and y. So this is using the original data set. And then what you have to do is, now you can apply the Boxcox transformation. What you have to do is, we will give a variable name for this, since it's Boxcox transformation. Let's say it's BC. Now here, what you have to do is, we are using the inbuilt function Boxcox. So in order to use this inbuilt function Boxcox, you have to you have to load a package in R. The package name is mass. So in this case, you know now how to load packages. So you have to go to packages, and then first you have to install package. You have to go to install packages and select the package, and then you have to go to packages and load package. Then your package will be loaded to R, or else you can use the function library and you can give the name of the package. Here we are going to use mass. So here I have already loaded my package now to R to use this Boxcox transformation built-in function. So what I'm going to do is, I'm going to give a name for the variable as BC, and I'm going to use this Boxcox inbuilt function, and within brackets we have to give the model. So our model is the regression model between x and y. So when you run this, you will see a graph like this. So this graph is showing you the optimal lambda value to perform your Boxcox transformation. Now you can see when you take this function, the maximum value for lambda occurs somewhere here. So it's between -1 and 0. So it should be a minus figure and it's not in the middle. So it's towards your right-hand side. So it should be less than -0.5. So we need to find this lambda value now to perform the transformation. So this is the now when I explained you the theory, I showed you an equation how to find the optimal lambda value when you are using the Boxcox transformation. So here what they have done is they have fitted the regression model and they have obtained the sum of squared errors values, and then they have changed the lambda value and they are checking for which lambda they can get the maximum value for that function. So that here in this case, we can see lambda is somewhat closer to -0.5, and in that case we can find the optimal value for lambda. So in order to check what is this value, now here it's just a chart. You can just, when you're doing analysis, you can just incorporate this chart for your analysis. And then you can check actually what is this value. So to check what is that value here, that is the lambda value. So we are going to check the lambda value that is coming from the Boxcox transformation. So here, that is actually, we are checking the coordinates of this chart. So when you use this function, you can see we can obtain the lambda value. So you can see it's -0.42. So the optimal lambda value for this is -0.42. Now we know what is the lambda value. So we can perform the transformation for the new model. So let's say when you take the transformation, you are using, let's say, y to power lambda -1 divided by lambda as your Boxcox transformation. So it depends. You can use any transformation you like. So in this case, if you are going to use that transformation here, so I'm going to take, this is the new model. For the new model, what we are going to do is we are going to fit a linear model. And in this linear model, the y variable now we have to change. So the y variable that we are going to use for the linear model is, let's say, y to power lambda, because now we know what is lambda, right? Y to power lambda -1, and let's say we are going to divide it by lambda. So this is the y variable that we are going to use here. And with this y variable, we are going to use the original x variable to run the model. So now you can call the new model and see what will happen to the new model. So I'll take a summary of the new model and let's check what has happened to the new model. See, now the intercept is also significant in this case, but the coefficient is not significant. So we can see what are the other things that you can do with the heterogeneity there and all. Anyway, this is how, if you are going to use the inbuilt function Boxcox to perform the Boxcox transformation, you can use this with R. So when you are doing your final year research also, you can use this built-in function to perform Boxcox transformation. Okay, I'll stop it to share the note now. Okay, so that's how we perform the Boxcox transformation. You have any questions regarding that? Okay, so then we are going to talk about another test, that is to check whether the errors are having a constant variance or not. So that's the White's heterogeneity test. The importance of this test is this is not depending on the normality assumption. Even though your data set is not normally distributed, you can use this White's heterogeneity test to check whether your errors are having a constant variance or not. So how to do this? Now imagine this is your regression model. So you have your response variable y, you have the intercept beta 1, and you have your independent variable x2 and another independent variable x3. So we know how to fit a regression model using these two variables x2 and x3. So this is the basic format that we can use in order to fit a regression model using these variables. So in this case, if you are going to perform this White's heterogeneity test, what you can do is first you can take your independent variables and your response variable and fit the regression model. And after fitting the regression model, what you have to do is you have to obtain the residuals of this fitted regression model. And then after obtaining the residuals, what you have to do is we have to take the squared values of this estimated residuals, and then we have to fit another regression model with all the possible factors. Now in this case, since I have two variables, all the possible factors would be, I can just put an intercept, then I can take x2, x3, then I can take x2 squared, I can take x3 squared, then I can take the multiplication between x2, the product between x2 and x3. So we take all the possible factors, and as your response variable, we have to take the squared values that we have, squared error values that we have obtained from the original model, and we have to run this regression model. And in this case, when you run this regression model, what you have to do is you have to check the R squared value of this regression model. So in this case, when you check the R squared value, the null hypothesis that we'll be testing here is there is no heterogeneity. And here the alternative hypothesis is there is heterogeneity. So what you have to do is you have to take the R squared value and then multiply that R squared value by n. N is the number of observations in your sample. And then this n into R squared, this is having a chi-square distribution. So the degrees of freedom, they are equal to the number of regressors in this auxiliary regression model. That is the regression model that you fitted using the squared values of errors. So as for this example, you can see here you have one term, here 2, 3, 4, 5 regressors we have used. So based on this example, the degrees of freedom would be 5. So then what you have to do is you have to compare the calculated value with the table value. If the calculated value is exceeding the table value, we can reject H naught. That is, if you reject H naught, there is heterogeneity. That is, the errors are not having a constant variance. So we can do that. That is how we check the heterogeneity using this White's heterogeneity test. So let's look at this example. It says an economist wants to test the relationship between housing expenditure on income of a person, and he collects data from a sample of persons. Following table contains data of 8 persons under this study. So here you have a small sample which consists of 8 observations. And here you have one variable, housing expenditure, and you have their income. So we know income is, we know the housing expenditure is always depending on income. So you can take your Y variable as housing expenditure, and you can take your X variable as income. So the first task that you have to do is you have to test whether heterogeneity is present using this data set, using the White's heterogeneity test. So let's do this using R. I'll show you how to do this using R. Okay, the first thing, now I have taken this, I have copied this data set to an Excel sheet, and I have saved that as a CSV file. That is the first thing that you have to do. So after saving that, we have to import our data set to R. So now, by now we know the function that you have to use to import that to R. So that is the read.table function. So here I'm going to use file.choose and header equal true, and we want to separate all the values. So I'm going to, this is my data set, select my data set. Now let's see whether I have imported my data set to R. Okay, so we have all 8 observations for the housing expenditure and income. So the first task, if you're going to perform White's heterogeneity test manually, is to obtain the residuals, right? So to obtain the residuals, what you can do is you have to first fix the regression using this, the original regression model using these original variables. So I'll take this, the original model that I'm going to fit as fit1. So I'm going to use the function LM to fit the regression model. So here my Y variable is housing expenditure. So I'm going to copy it here. So that is housing expenditure. With that, my X variable is income in thousands. And here you have to give the data is coming from my data set. And here I'll just call a summary and see what has happened to this regression model. That is fit1. Yeah. You can see the intercept is not significant, but the beta 1 value is significant here. So let's see what is our task is to check whether the heterogeneity is there. That is whether the errors are having a constant variance or not. So for that, now we have fitted the regression model using our X variable and Y variable. Now I have to obtain the residuals. So I'm going to use the variable name as res, and I'm going to use the inbuilt function residuals, and I'm going to give fit1. Now I have stored the residuals to this variable res1. You can just call res and see here. Now these are the residuals. So if you are going to do this in your exam manually, since you do not have R, what you have to do is first you have to fit your regression model and find your intercept and your beta 1. And then you have to find the residuals. How do you find the residuals? You have to take yi minus yi hat values. That is, you have to take the original y values and then you have to subtract the yi hat value. So the yi hat values you can estimate using the equation. That is when you know the intercept and when you know the beta node. For an example, if you take the first, in this case, the first observation here, y value is 12.18 and x value is 17.8. So what you can do is, here if you want to take the yi hat value, now when you take your data set, the equation is this. So what you can do is to take the first, let's say y1 hat, what you have to do is you can take the intercept is 1.80418. This is when, if you are doing manually, plus beta 1 is 0.65913 into x variable is 17.8. So from this you can find the yi hat value. And in the original data set, for the first observation, the y value is 12.18. So then what you have to do is here, you have to take 12.18 minus this y1 hat value. And then this is the value of the first residual. So you can see we have obtained the same answer using the inbuilt function, that is minus 1.35. You get the same answer even if you do it manually. So in the exam, if I ask you to do it manually, this is how you do using your calculators, right? So now in this case, we have obtained the residuals. Now to perform the White's heterogeneity test, the second step that you have to do is you have to take the squared values of these residuals as y. So I'll just take y squared. Let's take y_2 as y squared. So that is the squared values of these residuals. So I'll store the squared values of these residuals to this variable. Now what you have to do, you have to fit another regression model, let's say fit 2, using the same LM function. You have to use this squared residuals as your y variable. And then what you have to do is you have to use all the other possible factors in your data set here. So in this case, since you have only one x variable, right, the factors that you can include is only x here, because you can include the intercept and you can include only x variable because we don't have any other factors in this case. So because of that, what I'm going to do is here I'll take my variable as the x variable is this. So my data so now I can use a summary for the fit 2. Yeah. So you can see what has happened now here. When I use this, when I run this auxiliary regression model, now I have the intercept and I have the x variable here. That is the only factor that I can include since I have only one variable. And then here I have the response variable is the residuals, and I have taken the squared value of those residuals. So in this case, if you look at the R squared value, that is 0.72. So what is the calculated value? Calculated test statistic value. So I'll take calculated test statistic value here. So that is, you have to take the number of observations, n. In this case, we have 8 number of observations, and you have to multiply that by the R squared value. So in this case, I'll take the R squared value here. And if you check the calculated value, it's 5.8048. So this is the calculated value. And now we have to compare this calculated value with the chi-square table value. So here, if you look at the number of regressors, in this case, you have only one regressor. Right, I'll show you the note again for you. See, now in this case, we have only only one variable, and in this case, okay, there's a small mistake I have done in fitting the regression, the auxiliary regression. Let me correct it. So here, when you fit the auxiliary regression, the small mistake here. Now, since you have only one variable, you have to include all possible factors. So that is here, the income in 1000 is your X variable. So you can include that and the intercept, and also you can take the square term of that variable. So I forgot that actually. So here you have to use this X variable, and then you have to take the squared term of this variable. And now you can check the summary here. So you can see here you have the X1, X variable, and the yeah, so this is the, so we have fitted both values. We have taken the, in this case, so let me rename this variable using X, then that will be clear for y'all. So here I'll take this income data as, let's say, XX. So this is the income value. So what I have done here is, in this regression model, so we are going to fit the regression using the squared values of the residuals. That is the squared values of the residuals, that is y_2. And then what I'm going to do is to fit a regression using this XX variable, and all, when you consider all possible factors, you can include the squared value of that as well. And then what you have to do is you can just take this R squared value of this fitted model. So I'll take it as fit 3. So in this case, when you take the R squared value of this one, so here you get it's 0.7253. So what you have to do is to take the calculated statistic value. So here you can take, you have 8 number of observations multiplied by the R squared value, that is 0.7256. And then let's call this calculated value. So that is 5.80. So now in this case, you have to check this calculated value with the chi-square table. So when it comes to the degrees of freedom in the chi-square table, now here you have X and X squared. So number of regressors you have is 2. So you can read that value from the chi-square table and compare that. If the table value is exceeding from this, if the calculated value is exceeding the table value, you can reject H note. So in this case, if you check the table value, you will see table value is less than the calculated value. That is, table value is close to 1 point something. Just check the chi-square table and see. So in this case, this calculated value is 5 point something. So here we saw it's 5.08. So that is, we can reject H note. So if you are going to reject H note, we are rejecting that. That is, we can conclude there is heterogeneity, that is the variance of these error terms are not having a constant, not distributed in a constant band. They are not having a constant variance. So in that case, we have to come up with a remedy to overcome this issue. So if we have this heterogeneity, but one thing that we can do is we can carry out this Boxcox transformations and see what we can do. Whether when we apply a transformation, is there any change in this data? So you can use lambda value as -1, lambda as 0, lambda as 1, and check what will happen to your data set. So I showed you here with the lambda value, these are the most common transformations that you can use. So in this case, when you are using lambda as -1, you can take your y variable as 1 over y. So if you are taking lambda as 0, you have to take log y as your y variable. So if you take lambda as 1, you have to take just, this is where if the lambda is equal to 1, that is the original y variable. No need to do any transformation. So in this case, you can use these values -1, 0, and 1. So if you are using 1 means that is the original data set. We have already fit a regression model with that. So you can check what will happen when you take lambda as -1 and when you take lambda as 0. So let's check it with R. So this, I hope you didn't see my screen. Now in this case, here, this is the transformation that I talk about. So here you have to, now since when we conduct the White's heterogeneity test, we can conclude that there exists heterogeneity, that the error variance is not constant. So in this case, you have to, as a remedy, you can use the Boxcox transformations and see what will happen. So here they have asked you to use the lambda value as -1, 0, and 1. So when you check the most common Boxcox transformations here, when lambda is equal to -1, you can take y as 1 over y. When lambda is equal to 0, you can take y as log y. When lambda is equal to 1, you can take y as, that's the original y. So for the when lambda equal 1, we have already fitted a regression model, and we know for that model there exists heterogeneity. So now we have to check when we use this -1 for lambda and when we use 0 for lambda and when we use this transformation, what will happen, whether we can overcome this heterogeneity. Let's do this with R and C. So actually, when you perform this White's heterogeneity test in R, you have inbuilt functions for that as well. But I'm just showing you how to do this manually, because in the exam, you have to do these things manually. So what you have to do is now we have fitted our original model. So in that original model, here it's fit 1, right? This is our original model. So you have your intercept and we have X variable that is income in thousands. But the problem is we have heterogeneity here. So let's apply a transformation and see. Let's take lambda as 1. So you -1. So you can use 1 over y as your transformation. So let's take trans Y as my variable. So what I'm going to do is I'm going to take this housing expenditure variable, which is coming from my data. So I'm going to take 1 over this variable, right? So now I have 1 over y values that I have saved it as this trans y variable. Now let's see. Now you can fit a regression model using this y variable and your x variable. So your x variable is income in thousands. So here, let me take this as capital X. That would be easy. My data, I'm going to rename my x variable as capital X. So now here what I'm going to do is, I'm going to fit a regression model. Let's say model 1 for the transform data and this Boxcox transformation data, so that if I take this model like this, and I'm going to fit a linear model using this trans y variable and capital X variable. So here I can call model summary. So I can use the name of my model and then I can call model summary here. So you can see in this case, actually both the intercept and the beta 1, they're highly significant. The only thing that we have to check here, whether we can overcome from the heterogeneity. So what you have to do here is, now we have to store the residuals of this model and then we have to run the auxiliary regression model. So what I'm going to do is, I'm going to take the residuals of this trans model. So that is, I'm going to use inbuilt function residuals, and then the name of my model is this. Now I have stored the residuals here. So I'm going to obtain another model. Let's say model 2. It's a linear model. So what I'm going to do is, my y variable would be the squared values of these residuals. The squared values of these residuals. And for my x variables, I can use capital X and also capital X squared. Right? And now I can just call the summary of this model. So that is model 2. You can see the R squared value is somewhat low here, and the model, the variables are also not significant. So what we can just do here is, now to take the calculated test statistic value, here you have 8 observations. 8 you have to multiply by the R squared value. So in this case, it's 0.1824. So actually here, if you compare this with the table value, table chi-squared value. Now I'll show you the table chi-squared value as well. I'll show you the table chi-squared value. Okay, so this is the chi-square table. Yeah. Can you all see the table?
Yes.
Yes.
So here you can see, now in our case, the degrees of freedom is equal to 2 because we have two regressors, x and x squared, right? And here we can read, since we are using 0.05 as level of significance, you can read 0.95 from the first row. And here you have 0.1. Okay, so the table value is 0.1. Let's look at the calculated value again. So the table value is 0.1. Okay, so the here the table value is that is equal to 0.1. Right? Now what has happened here? Now in this case, when you use lambda as -1, you get 0.1824, which is higher than the table value. So that is, in this case, again, you can reject H naught. So if you are rejecting H naught, that is still heteroscedasticity is there. So that is lambda equal to -1 is not a good transformation. Okay, so you can check what will happen when lambda equal to 0. So as for the common transformations, when lambda equal to 0, you can take log y as the transformed data. So in this case, what you can do is, now here, if you use right, so here what I'm going to do is, I'm going to use the I'm going to transform this data, and here what I'm going to use is, I'm going to take the log values. Let's say log values of this as the transform y value, right? And now we can do the same process here. First, you can fit a regression model using this transform data, right? And the x variable. So here trans y2 is the log values. And then you can obtain the residuals here. So I'm using the same commands, right? So I'm using the residuals here of this model. And then I'm going to fit another model using the squared values of these residuals, and x variable and x squared. And then I can check the model summary here. So in this case, you can see your squared value is this. So we can just check what is the calculated test statistic, that is 8 into 0.04446. So that is 0.35568. So what has happened? What is our table value? Table value is 0.1. Again, our table value, you can see it's the calculated value is higher than the table value. So still we can reject H naught. The heteroscedasticity is there. So you can keep on doing, you can change your lambda value, you can change transformations and see what is happening to your model, whether you can overcome these the heteroscedasticity and what will happen to your normality assumption and all. So this is how you conduct these Boxcox transformations and also the White's heterogeneity test manually. So if you are using R, if you have a take-home assignment, no problem. You can use all the inbuilt functions. Even when you are doing analysis for your own project, you can use inbuilt functions. The only thing is in the exam, if we have no way to assess you using R, since if you get only the theory paper, so you have to know how to do all these calculations manually, right? So with that, do you have any questions up to that point? If you have, you can raise them. Okay, so sure, I will, one request to upload the last week lecture. Sure, I will upload the recordings by today. Anything else? So I'm planning to discuss another tutorial on Friday session. So I will upload that one as well today, a tutorial or an assignment. So I'm not taking marks from that, but you can do it and submit. Before Friday, we'll be discussing the tutorial on Friday.